Covalent compounds or molecules, we're going to be looking at Lewis dot structures and shapes and VSEPR theory and formal charge and all these wonderful things. Now, today's lesson will involve some review from Chem 1, but there will also be some new introduced concepts that you have not seen before. So it's kind of a blending, it's upping the ante a little bit, going a little bit more deeper than what you've already experienced from what you learned in Chem 1. Going over our learning targets and the enduring understanding. The enduring understanding is for all of these sections, 2.5, 2.6, and 2.7. Now, molecular compounds are arranged based on Lewis diagrams and the Valence-Shell electron-pair repulsion theory, or the VSEPR theory. It's much easier to state it that way. So in terms of Lewis diagrams, what are you expected to do? You're expected to be able to draw them and represent them with a drawing, following the rules and giving us the best Lewis diagram or Lewis structure or Lewis dot structure. You could hear it all different ways, but that's basically the same thing. Topic 2.6 is going to go into resonance, which you probably saw some of that in Chem 1 or Honors Chem. Formal charge, though, is something new that we don't typically go over in Chem 1, but let's take a look at what you're going to be learning there. You're going to represent the molecule with a Lewis diagram using formal charge. You're going to follow the formal charge rules now in order to do that. Lewis diagrams with an odd number of valence electrons. These are kind of exception weird examples, but we're going to go through one. So you're not caught off guard if they decide to put one on the AP exam like they did a number of years ago. You're going to be able to recognize Lewis diagrams that show resonance and draw Lewis diagrams that have resonance. Now this one, my bad though, this is supposed to be 2.7. By the way, that's the VSEPR and bond hybridization aspects of the chapter. We're really going to get into the shapes of the molecules, and that's based off of their Lewis diagrams, based off of the way their electrons are distributed, and talk about their hybrid orbitals and the different types of bonds involved in creating the covalent compounds and polyatomic ions. So we're going to define VSEPR theory. We're going to predict the molecular geometry of molecules and polyatomic ions. Now, molecular geometry is just fancy for shape. Bond angles, we're going to be able to look at the relative bond angles and identify those around the central atom. We're going to look at bond lengths, bond energies, and bond order. You know, we talked about those in the internuclear distance and potential energy graphs, but now we're going to apply them also to the Lewis dot diagrams and the ball and stick models, which are more three-dimensional in shape. Then we're going to declare polarity based on the dipole moments. And we'll look at the dipole moments to decide whether they cancel or not cancel, and the symmetry of the molecule and so forth as to whether the entire molecule is polar or nonpolar. And we're going to look at orbital hybridization and also the idea of sigma and pi bonds, what they mean. Sigma bonds are actually the hybridized orbitals. The pi bonds are also, they're delocalized between two p orbitals, but it's a different type of hybridization than sigma. And then we're going to also look at those and determine which bonds can rotate and which ones are fixed in a fixed position. So that's the gist of lots of learning going on, and they kind of all intertwine and mix as we go along. We're going to look at different shapes, talk about their features, talk about their angles, talk about their bonding, and kind of do it in a grouping way. That way, all three topics are kind of overlapping. I feel like that's a better approach than trying to do them separate. But let's talk about molecular shapes or molecular geometry. The shape plays an important role about its reactivity. So the way that they are bonded, the way that they are distributed around the central atoms, the outside atoms, or the ligands, that's what they're called, the outside atoms. You need to look at the bonding and non-bonding electron pairs. So bonding ones are these guys right here, in between the two atoms, a typical covalent bond, whether it's polar or nonpolar. The non-bonding electron pairs, you might know this by the word lone pair, Or, you know, say if we were drawing something like water. You've seen water drawn multiple times. These two sets of dots on the outside of the oxygen here would be considered lone pairs or non-bonding electron pairs. So we're going to be using these terms bonding and non-bonding or lone pairs. We're going to look at the way that they are distributed around the central atom so that we can predict the shape of the molecule. And you're probably familiar with some of these like linear, bent, planar, the T-planar, trigonal planar, the trigonal pyramidal, and then T-shaped is a new one. We don't go over T-shaped in Chem 1, but it's a new addition. As you can see, those chemists are so creative in their names because it literally looks like a T. My favorite one is the seesaw though, and if you've ever been on a playground where you've seen a seesaw, you're going to see why they call it that, but it's quite a not creative name for a shape, but basically that's what it looks like. All right, what determines the shape of the molecule? Well, simply put, we have to look at the electron pairs, whether they are bonding or non-bonding. So if they're a bonding one or a lone pair, because electrons repel each other. They are negatively charged particles, so they repel each other. That means they don't want to really be near each other. So they space themselves as far away as possible as they can around the central atom. And that determines and makes these small shapes that we see in the smaller molecules. What are electron domains? First of all, we have to define this with our example compound here, which would be like A, B, 3, E. Talk about why I would generally write that for this particular compound here. Refer to the electron pairs as electron domains. In double or triple bonds, all the electrons shared between the two atoms are on the same side of the central atom, therefore they count as one electron domain. So this double bond here, even though it's sharing 4 electrons, 2 pairs of electrons, it is still only considered one electron domain. One area of electrons. Really, that's kind of what it's talking about. An area of electrons is an electron domain. And we're referring to that around the central atom. So the central atom here is A. This is our central atom. And it has 4 domains. So let's look at the domains. It has 3 bonding domains where all of these are areas of electrons that are bonded. And it has 1 lone pair domain or 1 non-bonded pair. So this would be the 4th domain around the central atom. 1, 2, 3, 4 electron domains around the central atom is going to drive the shape of the particular molecule. And that's because of the Valence-Shell electron-pair repulsion theory, or VSEPR. The best arrangement of a given number of electron domain is the one that minimizes the repulsions between them. So why are they spacing out around the central atom and at as far a distance as they can get is because of these electron repulsions, you know, negative repelling negative. So lone pairs and bonded pairs are spaced out as far apart from one another around the central atom, creating a molecular shape. So as you can see here, you know, we have chlorine, 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 chlorine around our carbon. It is a 3-dimensional, they're trying to draw it 3-dimensional here, so you can see it's sort of like a mini pyramid looking thing. But these chlorines are spaced as far apart as they can get. This is a bonding, 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 and bonding pair, so 4 domains around this central atom. And this is the ball and stick model. We're also going to look at the Lewis dot structures. And there's a PhET simulation where you can play around with the ball and stick models. It's really good for 3-dimensional viewing as well. Since, you know, we're in the virtual environment, we'll be taking a look at that on Friday. This graphic is one of my favorites because it really kind of summarizes what drives the shapes. We have the electron groups up here, or the electron domains. If it has 2 electron domains around a central atom on either side, it doesn't matter whether it's bonded or non-bonded. If it has 2, it's going to be a linear shape. One example here is showing that you have 2 bonded atoms to a central atom, and that's why they do AX2 there. It's a general equation here where you're going to see a central atom with 2 ligands. Those would be the X's. But there are no lone pairs around that central atom, 0 lone pairs driving that shape. Now, if it has 3 domains, 3 things around the central atom, whether it's non-bonded or bonded electron pairs, 3 different electron domains. You have 2 possible shapes you can have here. One of them is the trigonal planar, or the flat triangle, where you have 3 bonded atoms, no lone pairs, 0 lone pairs around that central atom. So the generic would be AX3 here. The bent shape here, this is another one where you have 1, 2, 3 domains. You have a lone pair domain and you have 2 bonded domains. So that's a total of 3 still, so it still falls under the trigonal planar electron domain geometry, but you have 2 possible shapes. One shape has all atoms, the other one has 2 atoms and a lone pair. Well, that creates this bent appearance, and that's where we get AX2E. Now, the X2 is representing the ligands or the bonded atoms. The E, of course, is representing the lone pair there. Tetrahedral domain means 4 things around the central atom, 4 electron pairs. So the first one, of course, would be the tetrahedral shape, because there's 4 bonded atoms around the central atom, still with 0 lone pairs. We're always going to start off with the basic one, and basically the electron domain is, the first shape is always named after the electron domain because it has all the bonded atoms around it. But if you take off a bonded atom and add in a lone pair, now we're talking about the pyramidal ones, where we have AX3E, because you have 3 bonded atoms, 3 ligands, and then a lone pair. And then, of course, if you take off 2 bonded atoms and create it with 2 lone pairs, AX2E2, so 2 lone pairs here, still has 4 domains around it, but now it's a bent shape. This is more like your classic water molecule right here, under this particular tetrahedral domain with the bent shape going on. Gets more complicated when we get into our expanded octets, which would be the 5th and 6th ones here, where they have 5 and 6 electron domains, the bipyramidal, the octahedrals here. The regular bipyramidal, 5 atoms around the central atom. But seesaw, like I said, fun favorite here, 4 bonded atoms and 1 lone pair. And then T-shaped, 3 bonded atoms, 2 lone pairs. And then there's this weird linear one. So we have the normal linear where there's no lone pairs, but we have a weird linear one where you have 2 bonded atoms and 3 lone pairs. This is definitely in that expanded octet realm, and we'll go over expanded octets in next class, by the way. The tetrahedral one has 6 domains, so 6 bonded atom. I'm sorry, not tetrahedral, the octahedral. Octahedral domain has 6 domains around it. 6 atoms would make it just an octahedral shape. If you take off 1 atom and add a lone pair in that place, we end up with square pyramidal. So AX5E, and then 2 lone pairs ends up being AX4E2, and that would be square planar. It's like a flat square, basically. So these is basically outlines how we're going to build the shapes off of the domain. And it kind of follows a nice logical thing. As you add lone pairs, it changes the shape. Take off a bonded atom, add a lone pair, it changes the shape, and it follows this nice little sequence. All right, electron domains. One must figure out the number of domains around the atom. So here we've got ammonia, NH3. I start counting. I have 1, 2, 3, 4. So this is under that tetrahedral domain. Then I start looking at under the tetrahedral domain that has 4 things around the central atom, but one of them is a lone pair now, so that's going to alter the shape. So I would have to look at that in order to determine the shape. It'll be the tetrahedral domain in this case, but it's going to be the pyramidal shape because one of the domains around it is a lone pair. The electron domain geometry is not often the shape, so that's what I was saying here. First, you draw the Lewis dot structure. Here's the domain, which is tetrahedral, but then you look at your bonding domains. We have 1, 2, 3 that are bonded. That's 3, 1 lone pair, so this is going to be the pyramidal shape. So kind of steps into determining the shape of the molecule. But the first step, of course, is taking a look at the Lewis dot structure, so you know how many domains and you know what the domains are around the central atom. Once again, it becomes that nice little flow chart. So if we're looking at this example in the tetrahedral domain, take off a bonded atom, instead add in the lone pair here, the little lone pair. That changes the shape to pyramidal. And then if you have two lone pairs on here instead, and that's kind of how they signify them, as little clouds with dots in them, then it results in a bent shape. But these are all under the tetrahedral domain because they all have 4 electron parts around the central atom. Let's talk hybridization. Hybridization, valence bond theory. Now, when the atoms are bonding and sharing electrons, some of their orbitals have to overlap in order for them to get close enough and be able to actually share those valence electrons. So 2 ways orbitals can overlap to form the bonds. We're going to look at those ways. Here you have the idea of the internuclear axis. So that's like, one of the axes here. The sigma bond is going to be characterized by an overlap of s and p orbitals. And remember, s orbitals are spherical in shape, p orbitals are dumbbell shaped. Now they're going to overlap and between the 2 different atoms, and they form the single bonds. All right, so you're going to have an overlap of s and p orbitals between the 2 atoms in order to establish the single bond, and that's always on this internuclear axis. The idea of the pi bond comes into play when we're talking double and triple bonds. So every double bond has at least 1 sigma where you have the s and p overlap. The additional bond of the double bond, though, is where you have this pi bond. And you have the p orbitals, they're kind of these areas up here or on the other axis where there's overlap of the electrons being shared. They're slightly weaker than the sigma, they're weaker than the sigma bonds. No, but if you add a sigma and 2 pi bonds and have a triple bond, the overall bond itself is pretty strong, all 3 of them together. But the sigma compared to pi bonds are definitely stronger because they're on that internuclear axis, with more Coulombic attraction. So here, 1 pi bond in a double, and then there would be 2 pi bonds in a triple. Both the double and the triple must contain 1 sigma bond, where you have the sp overlap. So when you're identifying here, here's a single bond. That's just going to be a sigma. That's that sp overlap. If you have a double bond, one of them is a sigma bond, the other one is a pi bond. So you have an sp overlap, and then you have the 2 p orbitals overlapping. If you have a triple bond, one of them is the sigma, then 2 of them are pi's. Now let's look at it from like the delocalized cloud model. This is ethine. It's an alkyne, hydrocarbon with a triple bond in it. If you remember anything from organic chemistry. But what you'll see here is this first one is this hybridization and overlapping on the internuclear axis. The purple one is representing the sigma bond here. Now, these pink areas are the p orbitals sticking out from their dumbbell shapes. They have this ability to, delocalize, overlapping, sharing these electrons. And if this is a triple bond like we have over here in ethine, you have 2 sets of the p orbitals overlapping. These are your pi bonds. The purple on the inside and the internuclear axis there, that is going to be your sigma bond. So there's 1 sigma and 2 pi's in this triple bond of ethine. Over here too, it's also showing that there's a sigma bond between the C and the H because this is a single bond. So showing here that there's overlap, and that is also a sigma bond because it's just a single bond. So we have a C to C sigma bond here in the middle. We have a C to H sigma bond over here on the side, and then we have our 2 C to C pi bonds in the pink cloud area. Now let's start talking about the domains. We're going to start with the easiest domain, the linear electron domain. It's the most simplistic, it's easiest to work with. There are 2 electron domains around the central atom, and they're going to be bonded domains. So linear is not going to have lone pairs on the central atom. One type is going to have 3 atoms in the molecule, It was that like AX2 idea here. You have a central atom and then two ligands. That's one option for linear. There's also one other option for linear where you have two atoms. So like Cl2, where you have Cl to Cl like that. Well, if there's only two atoms in the molecule, you have a point A and a point B. The only thing it can be is a straight line. So that's the other option for linear. No matter what it is, you're going to have, if it's just two atoms bonded together, it's going to be linear. Now let's talk about drawing some linear molecules and going back to the idea of Lewis dot structures. And we're going to take a look at their hybridizing, how their orbitals hybridize, and be able to identify a bunch of different features about the molecule based off of its Lewis dot diagram. We could also draw the ball and stick model as well. So for hybridizing, when we're talking about the linear domain, in order to have overlap between, here's your central atom, here's your ligand, here's your other ligand, there has to be, around this central atom in order to have the overlap here, establishing the single bond. What happens is you have hybridization occurring around the central atom's orbitals. There's a mixing of the s and p orbitals. It yields two degenerate orbitals. So what that means is basically you have a spherical one and a dumbbell one. They mix together, they hybridize, they form a hybrid. So the blue and the red make the purple. It's making a mixture of the blue and the red. Now the mixture, of course, is resulting in a larger, more rounded purple lobe, similar to the dumbbell shape, but it's a little bit bigger and more rounder because you do have that S shape in there as well. So it forms these sp hybrids. All it takes is the two orbitals in order to hybridize, in order to bond two sides of this particular central atom. That's always going to be, linear is always sp hybrids. It only takes the two orbitals that have to hybridize in order to do the bonding here. Now what that leads to, this particular example is showing you BF2, whereas BEF2, beryllium, is the central atom here. So these purple ones are these sp hybrids that were formed around the central atom. The S and the P, one of the P's around the beryllium atom, they mix together and form this hybrid. And that's where they're going to share their pair of electrons and have that overlap region, sharing with one of the two P's of the F's over here. Now we don't have to go into that much detail. What you'll see though with this hybridizing and the shape leads to 180 degrees around the central atom. This area, of course, is a straight line, which is 180 degrees. It's the way they arrange themselves to be as far apart from each other as possible, according to the VSEPR theory. Now, yes, beryllium is a strange one. We're going to go over that exception in just a minute because it is odd. Before we get to drawing, though, I want to recall dipole moments and being able to declare polarity about the entire molecule. Now, we know we can declare the polarity of the bond by doing the electronegativity difference. However, when we're looking at the polarity of the entire molecule, we have to look at the dipole moments and the shape. So if dipole moments cancel, it's nonpolar. Last year, we just said, is it symmetrical? Well, the reason why we use symmetry in Chem 1, because the dipole moments are a little bit more complicated, but really the reason why it has symmetry is because the dipole moments cancel. Looking here at some of our examples like HCl, no, this one, the dipole moment goes towards the Cl over here. This is the more electronegative element. This side's going to be partially negative, this side's going to be partially positive. So no, this one's definitely polar. You have a direction, you have a dipole, you have two oppositely charged atoms on either side. Looking at the BF3 though, boron trifluoride here, as you can see, all of the dipole moments point away from the central atom. In this particular case, they're going to cancel. And you have all the same ligands because these are all F's on these outside So they're all equally pulling. There is no particular side that's positive, one particular side that's negative. So they cancel out. You have the nice symmetry going on. So this one would be nonpolar. Same thing with carbon tetrachloride, except for this one's a tetrahedral shape. All the chlorines equally pulling, the dipole moments cancel out, you get nonpolar. This is a nice example of the tetrahedral, though, that is polar. Why? Because the ligands are different. You have 3 H's and 1 Cl. Well, the Cl has the higher electronegativity, pulling the dipole moment pointing towards that direction, so this side's partially negative. Down here in the hydrogen area on the other side of the molecule would be partially positive, definitely polar. Not symmetrical, as you can see. We have this oddball chlorine here. Then you look at, say, ammonia, where the dipole moments point towards the N up here. And you could go back to the whole concept, too, of the symmetry on something like ammonia that does have, there is a lone pair up here on this part of the molecule. Remember, the lone pairs throw off the symmetry, so they create a particular directional way that the electron density is going, and therefore would be polar. So that's where we get, in one direction, we get the polar molecules. So by drawing it, we should be able to tell the polarity as well, based off of where the dipole moments are going to go. Now we're going to start drawing. So now we have to recall our rules about drawing Lewis dot structures. Then we're going to identify the components about the different diagrams. First one we're going to look at is carbon dioxide. It's a nice, easy one to start with, and we're going to, of course, also start with our linear examples and work through. This one's an exception, that's why I put it on here so I can show you how to draw it, because sometimes they ask about beryllium. And yes, it's a metal, and I understand that, but sometimes there's a few metals out there that actually do covalent bonding, because we know that, general rules aren't always followed exactly perfectly in chemistry. There's a few examples like this with the beryllium. But let's start with carbon dioxide. We know carbon dioxide pretty well, CO2. First things first, though, before you can draw any Lewis dot diagram, what do you need to know? First rule, what do I need to start with? Number of electrons. I need to count electrons. Count valence electrons of all the atoms in the compound. So I need my periodic table if you don't have all the groups memorized. How many valence electrons does carbon have? Correct, 4. Good. How many valence electrons does the oxygen have? 6. And since there's 2 oxygens in there, I have to multiply that by 2 exactly. So I get 4 plus 12. That's a total of 16 to work with. That's how many electrons I get to work with in this molecule. That's the first step. Anybody know what the second step is? I'm going to give you the first word. Determining the central atom. Very good. The central atom. And how do we determine that? What's the feature we look at first? In comparison to carbon and oxygen. Electronegativity, yes. So the least electronegative element, is typically the one that goes in the center. Now, in this particular case, like for hydrogen, remember hydrogen only needs 2 valence electrons to mimic helium, so hydrogen is not one that can ever be in the middle, ever. It is always, never going to be a central atom. There's fluorine too. Fluorine is never going to be a central atom because it can only form a single bond. There are some, though, halogens, though, in the expanded octets when you get to that third energy level that can be central atoms. So it's a little bit different there. But we're going for the least electronegative element. In this case, out of these two, carbon meets that. So carbon is the least electronegative element. Now, while I switch pen colors, you guys can figure out, what do I do next? What is the next step here? Attach the what? I'll give you the first word. Attach the ligands. Yes, okay, we're attaching the ligands. What are the ligands? They're the outside atoms, the ones that go around the central atoms. Now I'm going to attach them with single bonds. That's what I'm going to attach them with. And since I know this is in the linear domain, I'm going to draw it linear. And I know that because we say up here that this is linear, so I'm drawing it in linear domain. Now remember, like this, okay, that's 2 valence electrons that are being shared. If we had double, that would be 4 valence electrons. And if we had 3 lines in between, that would be 6 valence electrons. Each line represents 2 valence electrons. Now you could draw them as simple dots. I like the lines and the dots. That's how I do it. And you'll see it, you can see it both ways in the AP responses where they use the dots or they use the lines and the dots. So third thing there, attach the ligands with single bonds. Now we're on to the next one. After we do that, what's the next thing that we do? Satisfy, I'm going to give you the first word, satisfy. Which one do I satisfy first? The oxygens or the carbon? Yes, I need to satisfy the octets of the ligands first. Do the outside first. Outside first. So before I continue on, though, I want to make sure that I always work my way in. Work your way in is the better realm to go. We have 2, 4 that we've used, so I have to subtract 4 total because I haven't added up. So I have 12 left to work with. Okay, so I have 2 and 4, and then now I have 12 left. So if I want to satisfy the octets, I put the dots around here in the lone pair. So that's 6. Here's another 6 on this oxygen, like so. Those don't look like dots, those look like lines, but whatever. All right, so now I'm down to 0. And this is the case where I am running out of electrons. So, anybody know what to do when you run out of electrons? You run out, which we did. We are down to 0 today. Yes, we need to look for double and triple bonds. That's what we need to look to do to satisfy the octets. The oxygens are fine. They have 2, 4, 6, 8. But the carbon right here, 2, 4. Carbon does not have 8. Carbon needs to have 8 in order to be stable. So yes, we're going to do something called the coordinate covalent bond, where you take off a lone pair. Oops, didn't mean to do that. I erased my oxygen. And you double up the bond. So you remove a lone pair and then you create the double bond. Now, I want to go over something here because I'm not going to triple up this side. I'm going to tell you why I don't triple up this side. Group 14 central atoms, they typically form 4 bonds, whether it's, like that, or whether it's a triple and a single. Carbon group, they're going to form 4 bonds. They typically do not have lone pairs at all on the central atom. We're looking at group 15, which of course is the nitrogen group. They typically have 3 bonds and a lone pair. So you could do this, like so. You could do this, 1, 2, 3. 3 bonds, 1 lone pair. You're going to see if they're the central atom, that's how it works, unless it's an expanded octet. Group 16, which is the oxygen group, and especially for oxygen here. Oxygen likes to do 2 bonds and 2 lone pairs. So oxygen typically only forms these type of arrangement. Yes, there's an occasional crazy exception like carbon monoxide, but that's very rare to ever see oxygen do 3 bonds and 1 lone pair. It's typically 2 bonds, 2 lone pairs. So that's why I would do two lone pairs, 2 bonds on this side, and then come over here and remove this pair and create the other double bond on this side, because the oxygen is going to do the 2 bonds, 2 lone pairs, not a triple bond. And so this would be the correct Lewis dot structure then. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Everything has 8 now. So it's now in the octet rule. So if I wanted to draw the ball and stick model, drawing the carbon, maybe make them different colors, although carbon is usually black and oxygen is usually red. you would draw, you know, two bonds. They kind of round them to create your ball and stick model. So this would be the ball and stick model. Still is 180 degrees around the central atom. Now, looking at polarity, let's look at dipole moments here. Are there any dipole moments in our bonds? I know carbon, but electronegativity difference, oxygen's 3.5, carbon's 2.5. It's definitely a difference of 1. So it is a polar bond. Which direction do they go? Towards the oxygen or towards the carbon? Which one has the higher electronegativity? Yeah, so our dipole moments go, if I had to draw dipole moments in, this is how I would do it. However, they do have two dipole moments because there are two polar bonds in here. The carbon to oxygen is a polar bond. But they go opposite directions and they cancel out. So these are going to cancel. So overall, our entire molecule happens to be what? Yes, it's nonpolar. Good. So overall, we have a nonpolar molecule. We do have bonds in the molecule, but the overall molecule is nonpolar. It's symmetrical, exactly right. Okay, so we would go with that symmetry idea there. Very good. Now, another thing we would want to identify besides the angle and the polar, nonpolar deal is the type of bonds and hybrid orbitals in there. So first things first, we have a double bond here. So if we have a double bond here, that means we have 2 pi bonds. One of these is a pi, one of these is a pi. How about the other one in the double bond? What kind of bond is that going to be? Sigmas. So yes, now we have sigma bonds. However, our sigma bonds are going to be the overlap of the S and Ps. Remember, linear, the hybrids that are formed around linear central atoms are going to be SPs. So this is going to be 2 sp sigma bonds. So here's a sp sigma right here. Here's an sp sigma right here, and then there's the pi bond, which is the overlap of the p orbitals. So within carbon dioxide, we have 2 pi bonds, we have 2 sp sigma bonds. And they would want you to be able to pick those out of the molecule. We're going to keep practicing with that, so don't get worried. I mean, we're going to keep identifying it as we go. So if you didn't get it this go around, not to worry. Let's go ahead and take a look at our second example, HF. This one's much easier to draw. How many electrons do we get for this molecule? Eight. 1 plus 7. Good. So we have a total of 8 to work with. And there's only 2 atoms, so that's easy. They just attach. Okay, I've used 2. Now I'm down to 6. So where are those 6 going to need to go? Around fluorine, because fluorine needs more. Hydrogen's already there with its shared pair, so it already looks like helium. So this would be our diagram of our Lewis dot structure. If I wanted to draw the ball and stick model, hydrogen's smaller, or if you would see this as a ball and stick model, you would see that hydrogen is smaller. The fluorine would be larger. And it would just be the straight line here, right? Ball and stick model. The angle on this, of course, is going to be what? Straight line, always 180. Not a problem there. Now we need to look for polarity. What do we got going on here in terms of polarity? Dipole moment. Towards the F, good. Going this way. Exactly right, dipole moment. F is way higher, more electronegative, yes. So we do have a definite side that's partial positive, a definite side this side's partial positive, the F side's partial negative. So this is polar, a polar molecule. Now the only other thing that we would identify here is the fact that this is a single bond, so that's going to be 1 sigma bond. 1 sigma bond between them. And that would be it for identifying HF. Simple 2-atom molecule. Let's look at our beryllium example. This is the exception, and make a note of that. Put exception. Give it a big exclamation point, because we need to know our exceptions in AP. That's just the way they construct it. Beryllium is a metal, yes, but it does covalently bond sometimes. It covalently bonds, and it needs 4 valence electrons, so it shares 2 pairs of electrons. It's going to be one of those weird ones where it only needs 4 to be satisfied. With that in mind, I still want to count my electrons. So beryllium's in group 2, right? It's an alkaline earth metal. So that's going to be 2 from the beryllium. There's going to be, still 7 times 2. So this is 14 plus the 2. So we get a total of 16 to work with. Now out of B, E, and F, which one's the least electronegative element? Definitely. So that one we're going to put in the middle. Attach your ligands. Now I've used 4, so I'm down to 12. Oh, hey, isn't that nice? Who still needs electrons? Fluorine. So we're going to add 6 to this fluorine. All right, down to 6. Add 6 to this fluorine. Ugh. Terrible dots. And now we're down to 0. Let me fix those dots. I don't like those dots. All right. Beryllium has its 4 right here. Check. Exception rule. And each fluorine has 8. So we are now correct in our drawing. Degree across there, still 180. Once again, these are sigma bonds because they're single bonds. They're sp overlaps though because we're in the linear domain. The hybrids are sps. So here we have 2 sp sigma bonds. Is this polar or nonpolar? That's the last question, right? Let's look at that. Any dipole moments here? Towards the F's. Yes, there's 2 dipole moments, but they go away from the beryllium, so they cancel. So this is non-polar. Very good. So this is what we're looking at for the exception beryllium compound examples. Exactly right. You with me so far? We're doing okay. All coming back to you now, right? All this drawing stuff. All right, let's take a look now at the next, I believe we're on to the next domain. The trigonal planar domain. I like this one, yes. Here we go. We have 3 electron domains around the central atom. 1, 2, 3. Now you can have 2 situations, 3 bonding, 3 atoms, 3 ligands, or 2 atoms and 1 lone pair. So we have 2 shapes within this domain. We have the T-planar and we have the bent. All right, so pay attention to that. We're going to go over these examples. They're lots of fun, especially in the realm of the bent examples. Hybrids, though, similar to linear, you have to have some of the orbitals around the central atoms have to merge or mix or blend. I guess blend would be a good word. In this case, though, because you have 3 things that are going to be, attaching around the central atoms, or 3 domains around the central atom, you have 1 s, 2 p's, 1, 2, 3 orbitals have to merge. Okay, so we have 3 domains around the central atom. We need 3 orbitals to merge. So the blue and the 2 red make purple again. It's like mixing, blending. And once you can see too, They're a little bit larger lobes, once again, because the S is a little bit rounder and still kind of dumbbell shaped, but they've kind of formed this nice triangle around here with about approximately ideal bond angles of 120 degrees. This is flat triangle. So the T-planar shape, trigonal planar shape, is a flat triangle, is what we're going with. So you have 3 sp2s. Now that means 3 orbitals, 1 s, 2 p's, have blended together to form the hybrids around there. And they're all at a lower energy than they would be individually separated. So remember, we always go for the lower energy aggregate state, for the group here. So these hybrid orbitals actually, put them at a lower potential energy. Let's draw some examples here. We have formaldehyde, CH₂O, and then the boron example, which is another one of these exceptions. We'll get to that one in just a second. But let's look at formaldehyde. Step 1, count those electrons. How many electrons? There's 4 for carbon, 2 times the 1 here, because hydrogens have 1, there's 2 of them, and then we have 6 here. So that's a total of 12 electrons. Very good. Now what goes in the middle? Carbon, good. Hydrogen can't go in the middle, but carbon is less electronegative than oxygen. Now I just populate the ligands, and you can draw them however you want to, but I always go clockwise. I just think it's easier. You don't have to, and it doesn't matter if you put the oxygen over here and the hydrogen over here or what. I don't really care. All right, so I've used 2, 4, 6, down to 6 now. Which ligands still need electrons? Only the oxygen. Hydrogen's already good with its 2, already has the helium configuration. So we're gonna put 6 around our oxygen here. Oh, but now we're down to 0, we ran out again. What do we need to do here? Because carbon only has 6. Carbon is not stable. Double bond it, good. Take these off, create the double bond, good. All right, so now we have our nice double bond. Now if we're drawing the ball and stick for this, you have carbon here. Let's draw the ball and stick so we get a good idea of the flat triangle. Okay, here's the oxygen. And yes, I know I'm artistically challenged. It's okay though. It'll be all right. And the little hydrogens, because remember, they're smaller. There we go. But what you'd notice that this is kind of like a flat triangle. And the bond angles on this, ideal bond angle is going to be what? Around the central atom. 120 degrees, very good. That's exactly right. Any dipole moments to note here? Towards the oxygen, very good. We have one going this direction. It goes this way. So this is partially negative, this is partially positive side. Electron density spends more time around, or the electrons spend more time around the oxygen, creating a higher density. So is this polar or nonpolar? Definitely on the polar side. Now all we have to do is decipher the bonds. What kind of bonds we got here? And how many of them? And what are their hybrids going to be like around the central atom? Definitely have 3 sigmas. Good. We have sigma bonds. And we do have 1 pi. 1 pi bond. Good. Noted that one because we have the double here. So like this one's a pi bond. Good. Where the p overlaps. But what is the hybridization on the sigma bonds here? 3 domains. So yes, the 3 orbitals that have to merge are sp and 2 s and 2 p's. So now we have 3 sp2 sigma bonds and 1 pi bond for this particular molecule. Is it starting to get a little bit better? 3 domains, 3 orbitals merge around that carbon. So that's where that creates those purple lobed, lower energy hybrids. So we have 3 sp2 sigma hybrid bonds and then 1 pi bond. Let's look at boron. Oh, poor boron. Boron doesn't follow the rules either, so make this notable exception. Boron only wants 6 valence electrons in order to be stable. So boron goes for 6, not 8. If we go ahead and start drawing it, it should be pretty simple though, because we have 3, because it's in group 13, 7 times 3, that's going to be 21, so that's going to be 24 total to deal with. Boron's less electronegative, so we're going to put it in the center. And we draw our ligands. Very good. Now I've used 6, so now I'm down to 18. Oh, that's very nice. Who still needs electrons? Or which atom needs electrons? Chlorine, and each one needs 6. There's 3 of them, so guess what 6 times 3 is? Oh, it's 18. So let's go ahead and stick them on there. Okay, so now we have 0. Everything's happy because boron has 6. Because boron's weird and needs only 6. Yes, boron's going to only go for 6 here. I know, notable weird exception. Beryllium's 4, boron is 6. Let's note the angle. Ideal angle around here is going to be 120. Okay, got to know that bond angle. And is this polar or nonpolar? Nonpolar, because they have dipole moments. Don't get me wrong, but they go all directions out and cancel. So this is nonpolar. And if you drew it with the ball and stick model, it would be, you know, the flat triangle look. And 120, and I know that's not very good, but okay, whatever. Flat triangle, ball and stick model, 120 degrees over here kind of deal. Last thing to look at is the bond and the bond type. What do we got going on here? We have 3 sigmas, good. What type of sigmas? We're talking the T-planar domain. Yes, we have 3 sp2 sigma bonds. Exactly correct. Want to point something out and why we say ideal bond angle here of 120. Because in the example of like formaldehyde and also this one where it's like CH₂O. You're looking here, you do have a double bond in here. And that double bond does create a little bit more electron density. That electron density, of course, means these guys get pushed downward a little bit. So that narrows the angle here. It's only 111.4. Over here, though, it extends the angle to 124.3. Now, they're not going to ask you that specific of an angle. So if they were to say, and you identified it, that, oh, this is the T-planar domain, it is got the, flat triangle appearance, and they said what would be the approximate angle or what would be the ideal bond angle, you would just say 120, because they're not going to make you predict this. They might say, this might be a little bit less than 120 or a little bit greater than 120, but really what you're looking for is the mark of the 120 to be your gauge. You would not be, having to identify the specific angles here. They might say between the 2 chlorines right here, they might give you choices of greater than 120, equals 120, or less than 120. And you would know here, because of this bond density here, that they're slightly closer together, so that 120, it would be less than 120 in that case. And that's how you would figure out like a multiple choice problem like that. And that's why we talked about these ideal bond angles, because some of them are thrown off slightly by the lone pairs or by a double bond or something like that, where it's a little bit more electron density. The lovely bent examples that fall under this domain. And this is such a fun, wonderful exception too. Nitrogen dioxide. This is a brown gas, by the way. It's a very toxic brown gas that you wouldn't want to inhale or anything. Anytime I do a lab where nitrogen dioxide is produced, I have to put it in the hood, so the fume hood, so that it gets rid of all the nasty fumes, because you wouldn't want to breathe this in. And you're going to figure out why you wouldn't want to breathe this in, because it does lung damage. Why would it do lung damage? Well, we're going to check out its stability in just a second. Let's go ahead and start drawing. NO₂. Valence electrons. Let's take a look at those. How many does nitrogen have? 5. Let's look at oxygen. 6 times 2. Oh, that's 5 plus 12. That's 17. Anybody notice a problem here? It's odd number. Yes, that's bad. That's not going to be very helpful, right? But if you remember back when I was talking about the learning targets, there are some examples where there are odd number that do not follow the octet rule. So in a way, you would write this is also an exception. It's one of those oddball ones. You can kind of group it into the odd section. And this is really the only one I can think of that where you see an odd, but they might throw in an odd. And I don't want you to not know how to do it because you've never seen an odd before and realize that, oh yes, this can work sometimes. Well, let's go ahead and draw it over here. NO₂. So now I'm down to 13 because 2 plus 4, all right. Let's satisfy the ligands. Let's do that. Satisfy the octets of the oxygens. Okay, so that's 12. Now I have 1 left. When I have extra, what do I do with the extra? A good example of what to do with that. What do you do with that extra 1? Where does it go? On the central atom. So if you have any extra, they always go on the central atom. Now we're down to 0. But look at this. This doesn't look very good. Now, 2, 4, 5, that is definitely way unstable. So what I'm going to do is I'm going to go ahead and take off 1 and create a double bond here. So now we have more stability. 2, 4, 6, 7 around the lovely nitrogen here. 2, 4, 6, 8, 2, 4, 6, 8. But this causes a problem. I mean, it's unstable because it only has 7 valence electrons. But the problem is, for this particular structure, I put the double bond on this oxygen. I could have put it over here on this oxygen. So this molecule has what? Yes, this one has resonance. So when you have resonance, you have to draw both structures. So I have to draw the other one too. In this case, it only has 2, which is kind of nice. So I would draw the double bond this way. And yes, you have to put the little arrow between them because you're saying that this arrow between them is saying that they are equivalent structures. Now let's delve into the resonance idea here, and we'll touch on it at the end as well. But taking a look here, what does resonance mean? It means this other pair of electrons in the double bond isn't really between one particular nitrogen-oxygen. It actually evenly distributes amongst both oxygens and nitrogen bonds. So it's sort of like a delocalized hybrid over the entire thing. What does this mean? Well, it actually changes the bond order. So let's remember what bond order is. So say we have, our carbon dioxide. Those are double bonds. What's the bond order of this C to O bond? If it has a double bond, it's a bond order of what? 2. It's a bond order of 2. Very good. And, you know, if we had, say, the nitrogen, diatomic nitrogen, this would be a bond order of 3 because there's 3 bonds in there. And, you know, say we have water. It's a good one. These are bond orders of 1, right? Because they're single bonds, right? Now, how do we look at the bond order here when it's like equally split? Well, we have 1, 2, 3 bonds. 3 bonds being shared across 2 bonds, really. So really the bond order for this one is 1.5. So each nitrogen to oxygen is really like 1.5 bonds. Does that make sense? So it's like split. Each one has a full bond and then they have half a bond from the extra pair of electrons. So the bond order here in this resonance structure is 1.5. So it equally distributes. You get what I'm saying? Processing it a little bit. We're going to do another example, don't worry, so if it doesn't come to you now. But let's continue on with this example. This is a bent under the T-planar domain. So what's our angle going to be here about approximately? 120, good. And looking at our polarity here, what have we got going on for polarity? Oops. Is this polar or non-polar? Nitrogen is what? 3. Oxygen is 3.5. So yes, this one's definitely slightly polar, difference of 0.5. Now you probably wouldn't calculate off the top of your head, but I can. So the dipole moments go towards the oxygen, and they typically do. Another thing to remember, because you have this weird electron lone pair, remember the ones that have lone pair don't have symmetry, so they have dipole moments that don't cancel. So this is automatically polar because of that. And so this would be the partial negative side. This would be the partial positive side. It's just a slight one though. It doesn't have a huge electronegativity difference. So there's that. And then let's look at the bonds in here. We have 2 of the sigma bonds. And since this is under the T-planar domain where we have 3 electron domains, this is going to be 2 sp2 pi bonds. Sigma bonds, excuse me, sigma bonds. I wrote sigma and I said pi, but anyways, sigma bonds. But we do have this one that's equally spread over here. So we have 1 pi bond that happens to be delocalized. So you have 1 pi bond that's been delocalized over both sections. And that's what you would say here about the bonding. 2 sp2s, still in that domain of 3, sigma bonds, 1 pi bond that's delocalized. Yes, because remember, it equally spreads over both oxygens. So it's not in one particular nitrogen-oxygen bond, it's over both. That's what I mean by delocalized. Nitrite. Different example, same idea here, except for this is a polyatomic ion. This is nitrite. Remember, nitrate would be NO3. You know, you remember that one, right? Because you had to memorize that one, I know. But we're going to look at nitrite. Same idea here. We have 5, 6 times 2, that's 12. But what do we do with that charge of -1? What is important there? What do we need to do? Add an electron. So yes, so now we have 5 plus 12 plus 1. And guess what? That so conveniently gives us 18, which is the even number. So much easier to work with than the weird odd one. Now, yes, if you were to draw just nitrogen dioxide gas, you would draw it with just the 7 and it would be unstable, and that's why it's very damaging to lungs, because of course it's going to react with other tissues. It's one of those electrophiles where it's going to be seeking electrons. So here we still draw it the same way, down to what, 14. All right, satisfy the ligands. Just doing what I did for the other one. Okay, so that's 12, so now I have 2 left, and they go on the central atom. But still not complete here, 2, 4, 6. So we do need to do one of those coordinate covalent bonds and double up one. Sorry, that did not go very good. All right, but now this creates what for us? A problem. It creates resonance, so we have to draw the other one. Fun. When you have resonance, you have to draw all the structures. So when you get to something like nitrate that has resonance, now you have 3, because you have 3 oxygens, the bond can go over. All right, one more thing though I'm forgetting if I'm drawing a polyatomic ion. What else do you need in your drawing? Anybody remember? Brackets. I do need brackets. Bracket, 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 bracket. And then I need the charge on the outside. Very good. You guys remember. See, it's all coming back to you. So I need to have that as well. No, the nitrogen would want 8 still, and it does have 8 if you look here. 2, 4, 6, 8. 2, 4, 6, 8. So we do definitely still want 8 for the nitrogen. And that weird nitrogen dioxide example, it only was able to have 7. That's kind of why it's very reactive and poisonous and all that bad stuff. Looking here at the same deal, we would say there is dipole moments going towards the oxygens just slightly. So this is just slightly polar, like before. So very similar to the other molecule in that, yes, this would be like the partial negative side. This would be the partial positive side, because you'd have the dipole moments going towards the oxygen. Same thing too for the bond angle is approximately 120. Got that approximate 120 angle going on. And we still have the 1.5 bond order. That's going to happen because this bond is going to equally split across both. So it's like 1.5 bonds between each of the nitrogen to oxygens there. And once again, we have 2 sp2 sigma bonds. And then we have the 1 pi bond that's delocalized. The one delocalized. That looks terrible, but okay. The 1 pi bond that's delocalized over both NO bonds. So that would be the same, pretty much almost the same exactly, except for there's 2 dots on the nitrogen there, and you have your brackets in charge. So nitrite's very similar. A few little features are different. 4 electron domains around there. 4 bonded atoms is the normal tetrahedral shape. Take off one of the atoms and put a lone pair. Now you've got the pyramidal shape. The pyramidal shape. And then if you take off 2 atoms, 2 lone pairs, now we got the standard bent shape, which is what we know when we think of water. So tetrahedral, all are bonding. Pyramidal, 1 is a lone pair. Bent, we've got 2 that are lone pairs in this particular domain. So 3 shapes in the 1 domain. They do also have a hybridization now. We have 4 things around the central atom, so four orbitals have to merge together. 1s, and then 1, 2, 3 in the p's. So 1s, 3 p's still gives you this purple lobe, but now you're going to have 4 sp3s around there that have merged together that do the bonding, which gives us our ideal bond angle of 109.5 for the tetrahedral domain. It's ideal though because it's not actually the angle for all of the shapes. That is, if they can equally space around the central atom, it's going to end up being 109.5. There is a problem though with our lone pair situation. Lone pairs take up more space and they are more repulsive to other electrons. They cause more repulsions, they take up more space, so they decrease the bond angles. On your normal example of a tetrahedral, like the carbon, this is methane, carbon tetrahydride. We don't call it that, we call it methane. Where you have 4 bonded atoms, it's 109.5. You go and we have ammonia now where we have 3 bonded atoms and a lone pair. The lone pair takes up more space up here, so it pushes the hydrogens closer together. So now the angle decreases to 107. So on pyramidals, your angle is going to be 107. And then 2 lone pairs, like on water, pushes them even closer together because they're both taking up more space. So your bond angle on the tetrahedral bents, is 104.5. So pretty much, it decreases. Of course, this is the water example. You can see the non-bonding here showing that it's taking up more space rather than the bonding electrons, decreasing the angles on these guys. And you'll have to know the particular bond angles of the tetrahedral domain. So tetrahedrals are 109.5, that's the ideal bond. The pyramidals end up with 107, and then the bent shape ones are 104.5. Looks like we have time enough to draw one. This one should be easy. This is silicon tetrafluoride. This is your basic tetrahedral shape anyways, so let's go ahead and do that. Silicon is in the carbon group, so it has 4 valence electrons. Of course, fluorine's a halogen with 7, so that's 28. 28 plus 4, this is 32. Drawing regular tetrahedral ones are pretty easy. Which atom is going to go in the center? Yeah, silicon is definitely less electronegative than fluorine. All right, so that goes in the center. I attach my F's with single bonds, 2, 4, 6, 8, down to, 24? 24. Makes sense because each fluorine needs how many electrons? 6. So we add 6 to each, and there's 4 of them, so that's going to be a total of 24. So we're going to end up using up all of our electrons, and everybody's going to have an octet here. So this one's not too bad, pretty easy to draw. All right, so down to 0. Now, we kind of already talked about the bond angle here. 109.5 is your ideal bond angle. And since they're all the same bonded atoms, they are going to be 109.5. Now, this one's not on a plane. This one definitely is a 3-dimensional one. It's hard to draw the ball and stick model. I use those wedges and the lines and stuff to do the ball and stick model, and using the PhET simulation is much easier, but this is definitely a 3-dimensional shape. Let's look here at polarity. Do we have any dipole moments in this particular molecule? Fluorine's the most electronegative element on the table, right? So, yes, they all go towards the fluorines. But what does that mean in terms of our shape and cancellation? Symmetrical? Yes. Dipole moments cancel? Yes. So this is nonpolar. Definitely. Now we've identified the angle. Let's look at our bond types. What do we have here in our particular here in terms of the bond types? We all have single bonds, so we know they're sigma bonds. What's the hybridization on the tetrahedral domain? How many orbitals have to merge to the hybrid? 4 orbitals, so they're sp3s. So 4 sp3 sigma bonds. All single bonds in this particular molecule.